Here's a volume problem in polar coordinates, and I have a cold, so hopefully I won't sneeze all over the microphone. Find the volume between these two surfaces, and the claim is that polar coordinates is a good way to go with this. And the reason for that, of course, is that this is 3 times the quantity x squared plus y squared, or 3r squared. And this is just 4 minus r squared. So that says that this whole problem is going to be radially symmetric. There's no theta anywhere in here. The height does not depend on the direction. And that's almost certainly going to give a nice region in polar and a nice integral setup. So we want to know roughly what's going on here in terms of the picture. Now these are both pretty simple quadrics. This is a bowl going upward, and this is a bowl raised up but then going downward. And so here's one picture for that. The blue is the 3r squared, and the red is the 4 minus r squared. And you can see they intersect. And the volume in between is going to be everything above the blue and below the red. And I've graphed them out to radius equal to 2 here, and that's clearly too far. And so this is a very typical thing that we've already seen a little bit with integrals even before we did polar, and we're going to keep seeing over and over again. We have these two surfaces that bound a region, but what we really are interested in, or one of the main things we're interested in, is the curve of their intersection, an edge, not necessarily just the surface. So, well, that's not too hard to find algebraically. We just go ahead and set the two z's equal, and we get 4 minus r squared equals 3r squared. This is a book problem, by the way. I'm not going to tell you which book, in case you're just trying to... you're some student out there on YouTube trying to have me do your homework for you. Okay, so r squared is 1. Now remember, one thing I don't think I've emphasized with you guys is that even though in trig precal we occasionally let r be negative and we get these funky graphs like roses and stuff like that, when we actually use it as an integration variable, we never let r be negative. The reason is that we only want each point in the plane to only have one address. And we don't want to double cover everything. We'll get twice the right answer for everything if we do that. And so there's really a very good reason for only having r be positive here. So r is equal to 1. So here's another graph that I happen to have. Here's where I've only plotted these things out to r equals 1. And so here we can see that there's the roof and there's the floor. The roof is the 4 minus r squared, and the floor is the 3r squared. And the reason we really needed that intersection, that r equals 1, is because the floor plan is the shadow of this object, and the edge of the floor plan is the shadow of this circle. This circle is r equals 1, all thetas, and z equals 3, and it's the shadow of that, which is the unit disk, or the unit circle, in the xy plane, which is going to be the boundary of the floor plan. So the floor plan is just the unit disk, and so how do we set that up? It's going to be integral 0 to 2 pi in theta, and that's indicating that all directions are legal. It's completely radially symmetric. It's 0 to 1 in r, and the fact that those are constants is because it's a very, very simple region in polar. It's the simplest possible region in polar. It's the unit disk. And in particular that the radius that we go out to or start at does not depend on theta. And then the height, well, let's see. If we find the volume of this guy, for each point in the unit circle in the xy plane, we're going to be looking at the difference between the height of the top and the height of the bottom. We've done one like this before, where we just basically find the volume under the red minus the volume under the blue. Or another way to think about it is we just take a little column over any point in the xy plane. We take a little column that only extends between the blue and the red. And so that's going to be 4 minus r squared, and then minus the 3r squared, top minus bottom. It's really a lot like some problems in BC. And then, of course, r dr d theta. That's the area element. Okay. And I mentioned in class how if there's no thetas anywhere, you don't have to worry about doing anything complicated with the d theta integral. You can just get it out of the way right at the start. It's just going to give you a 2 pi. Just kidding. And then it's going to be 0 to 1, 4 minus 4r squared. And one good check is that it's not an exponent. One good check on this is that when r is equal to 1, this becomes 0. And that's good, because this 4 minus 4r squared is supposed to be the difference in height between the red and the blue, and that's going to be 4 here, the biggest, and then as r goes to 1 at the edge of the circle, it goes exactly to 0. That's why it was the boundary, because that's where the thing dies. And that's there's no d theta anymore. Talking and thinking at the same time. Okay, so the d theta has been integrated out for a 2 pi. Then this is a really easy integral, and I'm not going to finish it up because it's pretty easy, and the setup is the most important thing. Okay.